Alright, so we're just going to do wireless networks, continue on with the Network Foundations module on Hack the Box. And we're going to try and finish this out tonight. This should be pretty easy. We might even get to the other modules. So we're going to be covering wireless networks. So again, the author defines a wireless network as a sophisticated communication system that employs radio waves or other wireless signals. Other wireless signals to connect various devices such as computers, smartphones, and IoT gadgets, enabling them to communicate and exchange data without the need for physical cables. This technology allows devices to connect to the internet, share files, and access services seamlessly over the air, offering flexibility and convenience in personal and professional environments. So again, going to the pros and cons of wireless networks. Advantages, right? Mobility, ease of installation, and scalability. So again, like you don't have the constraint of physical cables that you would have with regular Ethernet. You just place an access point, and you have all these devices that are able to connect to it. And again, easily scalable. Not a lot of hardware. Disadvantages, right? You have interference, security risks, and speed limitations, right? When you're using an access point, let's say at home, you have your router that has a built-in wireless access point, and the bandwidth, let's say, is a gigabyte per second. You're splitting that bandwidth up by the amount of endpoints that you have in that network. So the speed limitations is a massive aspect of this. Again, security risk. We can see this in my channel when we're doing war driving. You can look at all the information about the wireless networks. Some networks also don't have proper encryption implementation, which just lets you be able to just read everything that is being transmitted through the air. And again, very prone to interference and jamming. So next thing is wireless routers. Again, I'm trying to take notes while we talk about all these. So again, wireless networks. I'm just gonna mention this TLDR for networks. Really just those pros and cons, that's really what I care about. I think it's pretty self-explanatory what a wireless network is, especially when we're talking about Wi-Fi, like 802.11 specifically. So pros again, mobility, ease of installation, and as for third is scalability. Cons. We have interference, security risk, and speed limitations. Cool. So now we're moving into a wireless, so Wi-Fi router. So again, a router, in general terms, is a device that forwards data packets between computer networks. In a home or small office setting, a wireless router combines the functions of routing and the wireless access point like we just talked about. So again, most routers at home, they're doing a lot of different things, right? They're doing the demodulation, modulation of signals, especially if it's coax. Doing the routing capability. You're doing the switching capability, right? Where it has multiple ports on the back. And then again, you're also doing that wireless access point capability. So your small or your home or small office router is really capable of doing a lot of different things. And then here we have, for example, at home, our smartphones, laptops, and smart TVs all connect wirelessly to our router. The router is plugged into a modem that brings internet service from the internet service provider. Below are the main components of a wireless router. And so again, we're looking at our WAN port, right? That's the external connection to the ISP, which connects you to the broader internet local area network, which just connects your local devices via Ethernet. You have the antenna, which is just the access point, as well as the processor and memory, right? So there's a computer within this device that's capable of doing all these computations to encapsulate and decapsulate all those packets in and out of the network. And again, covering NAT, it's capable of doing that. Okay, so we're aware, right? It's, so again, to cover what a wireless router is, right? We have routing. We have the access point, so the AP, or WAP, wireless access point. It's really the proper term there. Switch. And what's the other thing? And then modem, right? So demodulating and modulating signals. Okay. Turning it into zeros and ones on an analog connection. Oh, thank you for the subscription, Meow Chai Tea. I appreciate it. Cool. I kind of realized that camera's not really covering me, covering my face completely. And now I moved it too low. Should be good. I realize the camera thing is messed it up on this frame. Should be better. Better quality. Okay. So now we're just going to cover a hotspot, which again uses wireless capabilities. So a mobile hotspot allows a smartphone or other hotspot device to share its cellular data connection via Wi-Fi. Other devices, laptops, tablets, etc., then connect to this hotspot just like they would connect to a regular Wi-Fi network. A mobile hotspot uses cellular data, connecting devices to the internet via a cellular network such as a 4G or 5G. The range of a hotspot is typically limited to just a few meters. Running a hotspot can also significantly drain the battery of the device, creating the hotspot. For security, access to hotspot is usually protected by a password, similar to the security measures used for a home Wi-Fi network. To better understand this concept, we can imagine that we are traveling and don't have access to public Wi-Fi. We can activate the hotspot on our phone and connect our laptop to our phone's Wi-Fi signal. So I think most people have used a hotspot and are familiar with what capabilities it brings. But again, it's using that Wi-Fi to bridge that connection and then connecting via that cellular connection. So not really much to put. It's just really common sense. If you've used a smartphone, you've used the hotspot most likely. Alright, let's cover cellular towers, which I am not very familiar with. So a cell tower or a cell site is a structure where antennas and electronic communications equipment are placed to create a cellular network cell. This cell Any cellular network refers to the specific area of coverage provided by a single cell tower, which is assigned to seamlessly connect with the adjacent cells created by other towers. Each tower covers a certain geographic area, allowing mobile phones and other cellular-enabled devices to send and receive signals. So the individual cell is the tower, and that cell interconnects via the different towers. So cell towers function through a combination of radio transmitters and receivers, which are equipped with antennas to communicate over specific radio frequencies. These towers are managed by base station controllers, BSC, which oversee the operation of multiple towers. BSCs handle the transfer of calls and data sessions from one tower to another when users move across different cells. Finally, these towers are connected to the core network via backhaul links, which are typically fiber optic or microwave links. Cell towers are differentiated by their coverage capacities and categorized primarily into macro cells and micro/small cells. Macro cells consist of large towers that provide extensive coverage over several kilometers, making them ideal for rural areas where wide coverage is necessary. On the other hand, micro and small cells are smaller installations typically located in urban centers. These towers are placed in densely populated areas and fill the coverage gaps left by macro cells. To better understand the concept of a cellular network, imagine we are on a road trip, streaming music on the phone. As we move, our phone switches from one cell tower to the next to maintain connection. So again, like doing a road trip in a very rural area, and you notice that your cellular connectivity is going down, right? It's because you're either hitting like a black spot between cellular towers, or just the signal is really weak between these two cells. Is how they say. So just taking notes about this, right? Big takeaway, right? Individual cell is defined. So the cell in a cell refers to a specific area. So the cell is defined as the specific area of coverage provided by a single cell tower. Cool. Additionally, covered the difference between macro cells and micro cells. So it specifically said that macro cells cover several kilometers. So these want to say macro cell equals several. Again, we're not getting to specifics, right? This is very surface level. It's meant to be, it's network foundation. So it's really just trying to cover all these different bases at a very surface level. And so micro and small cells, how did it define those? So we know these are several kilometers. On the other hand, micro and small are simply just urban centers, right? So not a lot of coverage, but I can imagine that the micro and small cells have a lot of bandwidth capability, because if we think about like a city, right? And they have a bunch of micro and small cells, the area of coverage might be smaller, but the density of the amount of connections required is, the demand is a lot higher. So I can imagine that these micro and small cells are very capable in the amount of connections and bandwidth that they provide to the network. At least that's my takeaway. So here, frequencies and wireless communication. As mentioned earlier, wireless communications utilize radio waves to enable devices to connect and communicate with each other. These radio waves are emitted at specific frequencies, known as oscillation rates, which are measured in hertz. Common frequency bands for wireless networks include, and so now we're actually getting into the specifics of Wi-Fi. So again, regular Wi-Fi, two main frequency bands. You have 2.4 gigahertz and 5 gigahertz. You see this all the time at home when you're configuring your new access point. And then you also notice that certain devices want a specific frequency just because it might be faster or have better range, etc. So here specifically it says 2.4 gigahertz is used by older Wi-Fi standards, and we're looking at the IEEE standards, which is 802.11b, G, and N. Better at penetrating walls, but can be prone to interference, e.g. Microwaves and Bluetooth. On the other hand, you have 5 gigahertz, which is used by newer Wi-Fi standards, such as 802.11a, N, AC, and AX. Faster speeds, but shorter range. So again, that range aspect that I just talked about. You have faster speeds, but shorter range. If you only have one access point and you have a big space that you're trying to cover, 5 gigahertz might not do the job. And that's why you usually want to add multiple access points. Let's write down these frequencies, right? So these are the frequency bands. You have 2.4 GHz, gigahertz, and it is used by 802.11. And for anybody wondering what that is, that's just the IEEE standards. Which you have for different protocols, right? Wi-Fi is covered by 802.11. Ethernet is 802.3, I believe. So another one. Authentication, I believe, is 802.x. Is it's network authentication. So okay, so that's good. And then 5 gigahertz is used by 802.11. Again, what changes is just the standard, right? So this is A, N, AC, and AX, which are newer standards. So all these standards use both frequencies. I believe AC is one of them. And then, okay, we're going to cellular bands. Cellular bands, which again, I don't know too much about this side of things, but I think we're familiar with it, right? So we have 4G, which it says is LTE, and 5G. These ranges from lower frequencies to 700 megahertz to mid-range 2.6 gigahertz, and even higher frequencies for some 5G services up to 28 gigahertz and beyond. Did not know the difference in frequencies was that massive between 4G and 5G. There's an exponential amount of growth there. So different frequencies play crucial roles in wireless. Let me actually take note of that. So it's ranging from 700 megahertz to 28. Just really puts it into perspective. So different frequencies play crucial roles in wireless communication due to their varying characteristics and the trade-offs between range and speed. Lower frequencies tend to travel farther, but are limited in the amount of data they can carry, making them suitable for broader coverage with less data demand. In contrast, higher frequencies, while capable of carrying more data, have a much shorter range. Additionally, frequency bands can get congested as many devices operate on the same frequencies, leading to interference and degrade performance. To manage and mitigate these issues, government agencies such as the FCC in the United States regulate frequency allocations, ensuring orderly use of the airwaves and preventing interference among users. So in summary, on a typical day, we might use several forms of wireless technology. At home, our Wi-Fi router is using Wi-Fi at both 2.4 gigahertz and 5 gigahertz. We have our phone as well. When we leave the phone, our phone is using 4G and 5G networks by cellular towers. And while we're traveling abroad, we can also create our personal area network, which is called the PAN, through our hotspot to be able to share that internet connection and tether it to other devices. So we want to answer the questions now for this module. What types of waves do wireless networks use to connect devices? What type of waves do wireless networks use to connect devices? I'm blanking on this one. Are they asking about... they're talking about radio frequencies, I'm thinking. No, too abstract. Radio frequency. You think signal waves? No. What type of waves? And again, I usually want you to explicitly say something they mention. So this is radio waves. I said radio frequencies. So you just have to combine our answers there. What device combines the functions of routing and providing Wi-Fi coverage in a home network? So I believe they call that a wireless router. What is used by a mobile hotspot to connect devices to the internet? What is used by a mobile? I think... What do they want from this answer? Not sure what they want from this. They really want cellular data? I feel like that's... Spelled that. Cellular data, no. Did I misspell that? Let's see. Cellular data, no. Nope. Cellular data. Be a Wi-Fi. It says 2 words. It can't be Wi-Fi. I typed cellular data. Oh. I accidentally wrote down the wrong question, I think. Yeah, I did. I put it on question 4 instead of question 3. I was like, there's no way that's wrong. Okay. What structure supports antennas and communications equipment to create cellular network coverage? Cellular towers? Or are they asking about the BSCs? Which, is base station controllers. Did they want 3? No, this is 2 words. I thought it's base stations. No, I think they want something more simple than that. I think it might be a cell tower. Put cellular tower already, but yeah, they want cell tower. It's always very iffy with this. They want like one specific way. If you do the wrong acronym, then they won't take it. what manages multiple cell towers in cellular networks. And that's where it goes to the base station controllers. Controller. See, put an S wrong. Take out the S's, right. And then which frequency band is known for better wall penetration but more prone to interference? And that's gonna be 2.4 gigahertz. And they took it. That was a miracle. That is the format they wanted. Cool. So we are done with wireless networks. Let's mark that complete. Oh, is it gonna let me go? There we go. Network security. Moving to the actual security side of things. So let me write this down because it looks like this one's pretty long, right? Not horribly long. A lot of diagrams to take a lot of space. And demonstrations. Nope, my NVIDIA drivers are ready. So we are gonna do network security. Again, we're doing HTB networks. And again, if anybody wanted to jump in and do this while I do it and get some hands-on practice, all this is on Hack the Box Academy and it's all free. All modules that I'm covering on this channel are free, so don't have to pay a penny and you get to learn a lot about hands-on cybersecurity. So, very foundational concepts within network security, right? It's covering the CIA triad. The CIA triad, again, stands for confidentiality, integrity, and availability. Confidentiality is a concept that only authorized users can view the data. Integrity is that the data remains accurate and unaltered. We can trust that that data is accurate. That it is, if I sent it across the network, I know that the data stays intact. It can be assured. Availability is a concept on of being able to have the network resources, like that they're available when needed. And I don't know how far this goes into CIA triad, but the biggest thing is cybersecurity is this big war between availability and confidentiality and integrity, right? You can't max out all of them because it's just impossible, right? You can have a very secure network, but then it's less accessible, which means you might have a less productive network. But if you're dealing in an environment where you need a really secure environment, then you just have to deal with those trade-offs. And that's just a fine line as cybersecurity professionals that we have to navigate to understand, based on the environment that we're operating in, what that balance looks like. How much confidentiality, how much security do you need in that environment, while also maintaining the integrity of all your assets and data, and the availability of all those devices and data. So kind of went a little bit above what this is covering, but again, very foundational concept that is very important to keep in mind throughout your journey in cybersecurity. I'm just writing this stuff down because I'm trying to create some very comprehensive notes on foundational topics. So again, CIA stands for confidentiality. integrity, and availability. Okay, cool. So yeah, everything we're doing in cybersecurity as a defender revolves around this very concept of CIA. We go into firewalls, covering security, right? The more locked down the firewall is, guess what? The less things you can access, which makes resources less available. Okay, so firewalls. A firewall is a network security device, either hardware, software, or a combination of both, that monitors incoming and outgoing network traffic. Firewalls enforce a set of rules known as firewall policies or access control lists to determine whether to allow or block specific traffic. We can imagine a firewall as a security guard at the entrance of a building, checking who is allowed in or out based on a list of rules. If a visitor doesn't meet the criteria, e.g. not on the guest list, they are denied entry. And here we have an example of an open source router/firewall, pfSense, and large number of plugins and those packages give a range of capabilities. So in this a real world example of a firewall. This one just happens to be a software defined firewall. You can see it is running it locally on this Parrot machine, accessing it via localhost of 10.0.0.1. So firewalls operate by analyzing packets of data according to predefined rules and policies, commonly focusing on factors such as IP addresses, port numbers, and protocols. This process, known as traffic filtering, is defined by system administrators as permitting or denying traffic based on specific conditions, ensuring that only authorized connections are allowed. Additionally, firewalls can log traffic events and generate alerts about any suspicious activity. Below are some of the different types of firewall. And so, before we go into this, right, if we think of it, of this concept of firewalls intuitively, if you're using Windows, which most people use Windows for their personal computer, your Windows operating system has a firewall integrated into it. It's called the Windows Firewall. That is a software defined firewall. We think about the router, like how we were talking about how it's multi-capable, right? It's doing the switching, it's doing the wireless access point, it's doing all these different things. That also includes a firewall. So this is one of the other things. We got a bot on stream. Let me ban him real quick. These guys just keep sneaking in here. Banned. Got the ban hammer. Cool. So, just covering at a surface level, firewalls again is a network security device. And it can be at the operating system level. It can be a physical firewall located at the border of a network or between. It could be either hardware, software, a combination of both. So we're going to different types of firewalls. So here we have the first one. I'm just writing this stuff down. So the first one is packet filtering firewall. Packet filtering firewall. So packet filtering firewall description operates at layer 3 and layer 4 of the OSI model. Examines source/destination IP, source/destination port, and protocol type. So again, the reason it's at layer 3 and layer 4, right, is because we're looking at the packet source and destination, and then we're also looking at what port it is utilizing at the source and destination. So an example is a simple router ACL that only allows HTTP port 80 and HTTPS port 443 while blocking other ports. So essentially we're whitelisting HTTP traffic and HTTPS traffic from any source or destination for the network, and then blocking everything else. Now you're good for not getting the bot in time. You're good. I love the water though. Okay. So we know that 1 is operating at layer 3 and 4 of the OSI layer. We're looking at 2. You have a stateful inspection firewall. Cool. Thank you. Just gonna drink some water real quick. Alright. So 2, stateful inspection firewall. So again, it tracks the state of network connections, more intelligent than packet filters because they understand the entire conversation. An example of this is only allowing inbound data that matches an already established outbound request. So again, stateful inspection firewall, we're looking at the state of network connections. Rather than just looking at the header of the packets and segments. Three, we have an application layer firewall. Which in parentheses says proxy firewall. So operates at layer 7 of the layer 7, which is the application layer of the OSI model. Can inspect the actual content of traffic. So again, we're looking at that application level and looking at the contents, right? So we're looking at the data that's residing within these packets and determining if these packets are malicious and then blocking them. So the example again says a web proxy that filters out malicious HTTP requests containing suspicious patterns. We're talking about a DDoS, right? A smart firewall like this
should be able to tell, wait a minute, the same person, the same host keeps sending thousands of requests that look malicious to this one web server. The firewall should immediately deny that, and then any subsequent packets to prevent that DDoS from being successful. If we're talking about a password spraying attack or a dictionary attack or any kind of password attack where they just keep spamming passwords to the web server at a unreasonable rate, the firewall should be smart enough to be able to detect that that looks like malicious, like irregular behavior, and block that connection. So that's really what we're talking about here when we're looking at application layer. Now, all these examples are web firewall examples, but there are other protocols like FTP and SSH, which an application layer firewall might be able to inspect depending on the protocol. And 4 is the next generation firewall. That is NGFW. So the next generation firewalls, NGFW, combines stateful inspection with advanced features like deep packet inspection, intrusion detection/prevention, and application control. A modern firewall that can block known malicious IP addresses, inspect encrypted traffic for threats, and enforce application-specific policies. So I guess this next generation firewall, intuitively in my head, I like to think of it as is the new type of firewall, a firewall that is probably capable of inspecting at different or maybe all layers, and is able to utilize its knowledge of all these layers and what normal traffic looks like to determine what malicious traffic looks like. And it might be able to do this just through pattern recognition, maybe through some sort of machine learning. And then again, one of the capabilities I mentioned there was inspecting encrypted traffic, right? So building in those encryption keys that we're using within our network into the firewall so that it's able to look at the encrypted material in there. Again, double-edged sword, but this is just what security is about. Very intrusive, but it's just about keeping that network safe and secure. So firewalls stand between the internet and the internal network, examining traffic before letting it through. In a home environment, our router/modem often has a built-in firewall, software-based. In that case, it's all in one device, and the firewall function is inside the router. In large networks, e.g. business environments, the firewall is often a separate device placed after the modem/router and before the internal network, ensuring all traffic must pass through it. So here we have an example of a home network. You have your router/modem, right, that multi-capable device that includes a firewall, and the firewall is at a software level sitting between that internet connection, that WAN port, and the rest of the internal network. So now we are moving into IDSs and IPSs. Right. So again, I'm not sure if this is going to go into it probably, but IDS, intrusion detection system, IPS, intrusion prevention system. So one's detecting and the other one's preventing. So one is detecting and just doing that, right? It sees malicious traffic, it sees someone trying to brute force a password somewhere, it detects it, creates a log, and then sends it to, let's say, a SOC or something like that. IPS, it has rules set up, detects it, still doing the detection, but then it prevents it, right? So the prevention is an active security device, whereas the detection is passive. The prevention is going to see malicious connection and terminate it, depending on how it's configured. Whereas IDS just sees it, logs it, lets you know about it. So just different kinds of intrusiveness. And again, it's just going back to the availability, right? A lot of the times, these things are going to have false positives. Someone's going to have a very important web call and it's blocked. It says it's malicious traffic. Now this person can't call. You're directly affecting the availability of your systems. That one person, that one user is unable to use your services because of the security posture that you've created. Now again, every environment's going to have their own fine line of balancing between those two. I'm going to keep hitting that on and on throughout all these modules, because it's just a very subjective line that you have to navigate. Okay, so here again, IDS observes traffic or system events to identify malicious behavior, policy violations, generating alerts but not blocking the suspicious traffic. In contrast, the IPS operates similarly to an IDS, but takes action, right? It takes an additional step by preventing or rejecting malicious traffic in real time. The key difference lies in their actions. An IDS detects and alerts, while an IPS detects and prevents. They're the same thing I just said. The widely used Suricata software can function as both an IDS and an IPS. Here we see the user enable a detection rule, then begin inline monitoring. We're creating an alert here for TLS. Alright, so both IDS and IPS solutions analyze network packets and compare them to known attack signatures or typical traffic patterns. This process involves signature-based detection and anomaly-based detection. Signature-based detection being matching traffic against a database of known exploits, whereas the anomaly-based detection detects anything unusual compared to normal activity. And what you see a lot, and that's really the old-fashioned way of doing things, is the signature-based, right? You have a database, maybe open source database or a database that you're paying for, that offers all these different signatures, right? Usually in the form of hashes of what bad traffic looks like. Anomaly-based detection is being proactive in a way that we understand that there's threats that are not known, that have not been documented by a security researcher into a database, and the anomaly base is going more on the behavior side of things. Does this look normal? Does it look like a normal packet, right? Is this deviating from the normal, right? Because a lot of the time, every network environment is going to have a different kind of normal, and you as a security practitioner have to determine and create that baseline of normal network traffic. And that can be very, very tricky, especially when you're trying to create a baseline so that you can have an IPS, right? Because if you create a baseline that is inaccurate, and then now you're blocking all these network requests that are legitimate, and now you're impacting again availability of your systems. So I'm just gonna write down those two different processes. So one, signature-based detection. Two, anomaly-based detection. So yeah, again, when suspicious or malicious behavior is identified, IDS will generate an alert for further investigation, while the IPS stops it at that point. Okay, so let's go into different types of IDSs and IPSs. So really you just have two major categories. You have network-based IPSs and IPSs, which are often called NIDs and NIPs. Again, they're just network-based. Defines it as hardware device or software solution placed at strategic points in the network to inspect all passing traffic. So, again, on the network. Then you have host-based IDSs and IPSs, which is HIDs and HIPs. And then for this one, it just runs on individual hosts or devices, monitoring inbound and outbound traffic, and system locks or suspicious behavior on that specific machine. So, host-based. Now, you can have devices or systems, that sure we'll go into it maybe later into CMs, but you have systems that can ingest a lot of this traffic, a lot of this data from the network and actual individual endpoints to create a bigger picture, right? When you consolidate all this data, it gives you a different idea of what's going on in your overall network. One I have experience with is like an elk stack, on Security Onion. You can set it up so that you mirror traffic from your network devices, such as switches, and then have the elk stack ingest all that data and be able to visualize what all that data looks like. And then you're able to then create custom rules and alerts to be then notified of these kinds of things. Now, in that specific example, it's really more of a detective solution, right? It's not going to really do anything because this elk stack is isolated from the network. It's just there to collect data and analyze it. It's not there to actively prevent some of these things from happening. When we think about host-based IDSs and IPSs, most of the time we're thinking about like Windows built-in security, or if you have like some sort of third-party antivirus is what we call them. Reality, they do a lot more than antivirus. They're doing a lot of this HIDs and HIPs work. So IDSs, IPSs can be placed at several strategic locations on a network One option is to position them behind the firewall, where the firewall filters obvious threats and the IDS/IPS inspects any remaining traffic. Another common placement is in the DMZ, demilitarized zone, a separate network segment within the larger network directly exposed to the internet, where they monitor traffic moving in and out of publicly accessible servers. Finally, IDS/IPS solutions can also run directly on endpoint devices, such as servers or workstations, to detect suspicious activity at the host level. The following diagram shows an IDS/IPS positioned after the firewall. So here we have our little home network, our endpoints, the router modem, we have the IPS and IDS, then the firewall, and then into our wide area network. So some best practices for network security, defining clear policies, so consistent firewall rules based on the principle of least privilege, only allow what is necessary, regular updates, keep firewall, IDS/IPS signatures, and operating systems up to date to defend against the latest threats, regularly review firewall logs, IDS/IPS alerts, and system logs to identify suspicious patterns early, and use layered security, right? So use defense in depth, a strategy that leverages multiple security measures to slow down an attack with multiple layers. Firewalls, IDS/IPS, antivirus, and endpoint protection to cover different attack vectors. Then we have periodic penetration testing, which is testing the effectiveness of the security policies and devices by simulating real attacks. So that really concludes the end of this network security chapter here. Let's answer some of these questions, right? So what device monitors network traffic and enforces rules to allow or block specific traffic? I believe this one is referring to firewall. Which type of firewall operates at the network and transport layers of the OSI model? So I took notes of this, thankfully. That's the packet filtering firewall. Operates at layer 3 and 4. What advanced feature does a next generation firewall include beyond stateful inspection? Format, 3 words. How did they refer to the NGFWs? Deep packet inspection? It's probably the vocab word they're asking for, if I had to guess. Yeah. Which system generates alerts for suspicious network activity without blocking it? And the acronym. So they want an IDS. Which system not only detects but also prevents suspicious network activity by blocking it? An IPS. Again, active. What detection method involves comparing network traffic against a database of known exploits? So, this is signature-based detection. And that's done. That's all of it. And we're going to data flow. Interesting. Let me write this down. Data flow. Cool. So data flow example, based on the knowledge we have gained from the previous sections, the following paragraphs will show precisely what happens when a user tries to access a website from their laptop. Below is a breakdown of these events in a client-server model. So Again, we've covered the different kinds of networking models. So here we're looking at a client-server example, specifically when a user tries to access a website. So one, accessing the internet, right? Let's imagine the user is using their laptop to connect to the internet through their home wireless LAN. As the laptop is connected to this network, the following happens. So the laptop first identifies the correct wireless network / SSID. It uses WPA2 encryption or WPA3, and then the user must provide password or credentials to authenticate, and then the connection is established, and the DHCP protocol takes over the IP configuration. So checking local network configuration. When a user opens a web browser such as Chrome, Firefox, or Safari and types in www.example.com to access a website, the browser prepares to send out a request for the web page. Before a packet leaves the laptop, the operating system checks for a valid IP address for the local area network. So again, IP address assignment. If the laptop doesn't already have an IP, it will get one from the home router's DHCP server. And then the IP address obviously only valid within the local network. And the DHCP acknowledgement is just a packet sent to the DHCP server stating that the client acknowledges that they received that IP address, and then changes it within their own host. And we have DNS resolution. So again, we're just resolving that domain, the example.com, for its IP address. And again, this is just going to go to a DNS server. And we've already covered in the past what those specific DNS servers are called, in that whole chain of being able to resolve a DNS query. So for data encapsulation and local network transmission, so here we're going to start at the application layer of creating an HTTP request. The request is wrapped in a segment, a TCP segment most likely, because again it is HTTP. Then the TCP segment is placed into an IP packet, and then the packet is sent in a Ethernet frame with its physical addresses within that local area network. So when the encapsulated frame is ready, the laptop checks its ARP table or sends an ARP request to find the MAC address of the default gateway of the router, and the frame is sent to the router. Then we have NAT. So again, the NAT protocol is swapping out that header source, or sorry, not source, destination. It's changing the source, not the destination of the packet, to that public IP rather than the private IP, and it sends it from a specific port so that it's able to track what device within the network, which private IP did that request originate from. And the server receives a request, HTTP request for the website, and then it sends back another HTTP packet. And then you decapsulate that packet, and now you're displaying a website. And then here's a visualization of what we just talked about, right? So connect to wireless network, the DHCP request, DNS query, that goes outside the network, the DNS query goes out the network, and then we have a HTTP request, which gets natted and forwarded, is received by the web server, and the web server responds with the HTTP request, which is also changed at the NAT, and then now you're able to render that web page within whatever browser you're using. So that was pretty straightforward. Here we have a skills assessment. I didn't know this was part of it.
being tested on. Whether we're paying attention. I thought we were gonna do more modules, but I think we're gonna finish once we're done here. So I am a little bit tired. So skills assessment. Now that we're familiar with the foundational concepts of computer networking, it's time to apply them in a real-world scenario. And this guided assessment will explore the networking behind HTB Academy's lab environments. The assessment is divided into 3 chapters, but only the first 2 are required to complete the challenge questions and finish the assessment. The third is optional for those who want to explore further. So chapter 1, keep me in the loop. Whoa. Okay. They really thought this through. For the first chapter of this assessment, we will be showcasing the HTB, Academy Pwn box, which is a parrot box. And then again, she's talking about making it full screen. You launch it. You run IP config TAC A, which just shows you all the information about all your interfaces, including its physical addresses. Here is an example of IP config TAC A. You have your ENS3. Just use your wired connection, your Ethernet connection. Here's your IP, your net mask, broadcast, IPv6 is enabled on this interface. And where's the physical address? Here. That's your MAC address. This is your loopback, and it's connected via VPN, so this is a tunnel interface. Again, same information: IP, net mask, destination, and no MAC because it's a tunnel. Yeah. There's a lot to unpack here. We see 3 different unique IPv4s, some IPv6. However, one interface sends out from the rest. And that's the loopback interface.
What we are looking at is known as the loopback address, and it is always associated to the IPv4 address. So, just a good note, right? Loopback. Is always 127.0.0.1. That is always the IP address.
It's the IP address used when a device needs to send network data to itself. You may be wondering what purpose it serves. You said meow on a highlighted message. Maybe you're wondering what purpose it serves. There are actually several. It's often used for testing as a way to make sure an application is working as intended before going live on the network. It is also used by servers to keep certain services hidden from outside users. Think of an e-commerce website that utilizes authentication with its clients. Credentials and session cookies are typically stored in a database rather than have the database exposed to the public. It instead can only be accessed by the server itself. When a user attempts to log into the website acts as an API between the user and the database. The server queries its own database to retrieve information on behalf of the end user. So here we're gonna have the Pwn box make use of the loopback address by doing netstat tac TULN and P4. So netstat utility displays all network connections, routing tables, and interface statistics. With the options shown above, it lists all open or listening TCP and UDP ports for IPv4 in the format of IP:port. If permission allows, it may also show the name of the program responsible for each open port. Take a moment to review the output. Do you notice any services running on the loopback address? So right off the bat, you can see multiple. You have this one running on the loopback, 5901. This one, it's important to know port numbers. I don't know what this one is. I don't know if this one is. There's an SSH here. 111. You're running a web server here.
or it's reaching out to a web server here. Some ephemeral ports, NTP, 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 NTP. So NTP is running on the loopback. Okay, all these are internal services, so there is a web server running within here. So now we try to run TULP, which the difference is you take out the N. So okay, they removed the N, the output will be displayed host name and service. So now instead of having the IP, it's not resolving those DNS names, and it's actually showing you. So the loopback address just says localhost now. So that server we're talking about has this domain name. This is on the loopback, localhost, IPP, NTP, like I said, NTP, NTP. There's a bunch of NTP services running down there. With this information, we now have some insight as to how we are able to see and interact with the pawn box. Earlier in the module, we learned that protocol used when browsing websites is HTTP. We have the one on port 80. As we can see, the pawn box is indeed listening on port 80. This explains how we are able to make a connection via web browser. Subsequently, we can state with confidence that the IP tied to ENS3 interface is the public IP address of the pawn box. Remember, public IPs can be accessed over the internet, correct? Yeah, especially when they're out in the DMZ area. So we also see the BNC service running on the loopback address. BNC is virtual network computing. It's a protocol used for remote screen sharing and remote access. Since students can access a pawn-box desktop environment through their web browser, there's likely some form of port forwarding in place. And then port forwarding is a technique that allows traffic sent to one TCP/UDP port to be redirected to another, even across different machines. There's also another way to the loopback address can be utilized. Okay, so let's answer these questions. What IPv4 address is used when a host wants to send and receive network traffic to itself? So it's that loopback address, which is 27.27.0.0.1, sorry. What is the name of the program listening on localhost 5901? So we go back up here, and localhost 5901 is it doesn't really say PID / program name. What is the name of the program? I don't believe it comes up on here, if I'm looking at this correctly. There's no program name, unless that's just like an example. Is the program name literally use program name? I'm not seeing this answer here. Is there help on here? No. We'll skip this one for now. Which network interface allows us to interact with target machines in the HTB lab environment? Well, that's going to be your public, so your ENS3. Or was it ENS3? Or are we thinking about 10.0? Yeah, because it's offering us that through OpenVPN. What command line tool is used to configure network interfaces and display their current status? That's going to be if config tech a.
Is that what they did? If config tag A. Maybe they don't want the tag A. Yeah. What command line tool is used to display network connections? So that's that. Cool. So what is the name of the program listening on localhost 5901? That's a good question. 5901. I don't see a I don't see a name on here, it just says PID/program name. Not sure what's going on there. Because this one says X-Tiger, unless that is part of it as well too. 2814. Is that what the answer is? I guess that was the answer. I'm kind of wondering why that's out of order. I don't know, that's how Netstead did things. Okay. So the other one seems to be optional. That is interesting though, we're able to answer all the questions just doing that first chapter. The other one seems to be optional. I will do it. So having fun. At the beginning of chapter 1, we mentioned that Pwnbox is used to interact with target machines in our lab environment. At the end of chapter 1, we successfully investigated 2 out of the 3 available network interfaces. So the loopback and the public IP NS3. Now leaves one remaining interface. Ton 0. Based on its name, we can infer that it's a tunnel interface commonly associated with VPNs. So let's confirm this by checking which route the Pwnbox takes to communicate with the target. Okay, so we can do a route check, right? Let me write down these various commands. Forgot to write down that Netstack command. Let me verify. Attack T U L N P 4. And then the command we're running right now to verify what route we're taking for a specific IP address. We just type in IP route get and then the target IP. Cool. So our theory has been confirmed. All traffic to the target is routed through Ton 0. You can see that this is via def Ton 0. So VPN tunnel that connects the Pwnbox to the private lab. This allows us to interact with lab machines as if they were on the same local network. By using a VPN configuration file and software such as OpenVPN, we can configure our computers to connect to the VPN server. So let's begin our first interaction with the target machine. Typically always begin by using ping. So he's doing a 4 count ping there against the target service. Again, utilizing layer 3, the internet protocol. And here we're looking at the ping. And then if we don't specify count, yeah, it's just gonna keep going on forever. Unlike Windows, where it's not natively gonna ping forever, you have to explicitly say that. I've now confirmed that the target is reachable from attack host. A few things to note about the TTL and the time.
The TTL, which stands for time to live, tells us how many hoops or packets are allowed to take in order to reach the target. This rarely applies to devices on the same local network as us, but rather devices on the internet that require our packets to hop through multiple routers in order to reach their intended destination. The information next to time gives us an idea of how much latency there is on the network.
Okay. Then we have an nmap here. Now we can look at this open services.
So what does the FTP command use to retrieve a file? FTP command, I'm trying to remember off the top of my head. Is it not pull?
I thought it was pull. Yeah. That's gonna be on this chapter 3. So okay, we did an nmap. We see that 21 and 80. They anonymously log in to the FTP server. Their netcat via port 21. They're able to anonymous and then pass anything. Anonymous, anything. And then you're able to log in as anonymous. Caster channel, data channel. The command to get a file though, I was trying to remember. List. It's retrieve. RETR.
Bypass the request filtering found on the target machine HTB service and submit the flag found in the response. The flag will be in format HTB. Wait a minute. Bypass the request filtering found on the target machine HTB service. Did it say that we can do that? Let me see. What's the answer for this? I'm trying to see if this is something that will require going on the lab for it. Because they're trying to get us to bypass the request filtering found on the target machine's HTTP service and submit the flag found in the response. The hidden flag in the HTML.
Okay. This flag would have been right there. I see. Use netcat into it. Cool. Okay, it's getting late. But we are done with the network foundations module. Cool. So that finishes that module. Next we're gonna go into introduction to networking, but we're gonna do this one tomorrow. Nothing looks like a lot of it is stuff that we covered in that last module, but it's gonna go deeper into technical specifications and standards, into all of those theoretical topics we covered. So we'll start doing that tomorrow. We'll definitely won't finish it in one day. This thing always has like an estimate that is very conservative. We'll say 3 hours. I don't know who's doing these modules in 3 hours. It just took us an hour and a half to do three of those chapters. Okay. Appreciate anybody that was tuned in. This is gonna go into a VOD, so if you're watching this in the future, hopefully you're able to get something out of this. And yeah, just have a good day, have a good night. Peace out.